Let us take an electromagnet now. Two rectangular pieces of hand strip are placed side by side near to the electromagnet. Now, due to magnetic induction, both of the ion pieces achieve similar magnetic properties in their north pole and south pole, are induced at similar end of the ion pieces. If this pole of that ion piece becomes north pole, then the second ion piece also becomes north pole. Similarly, this end of both ion pieces become south pole. Due to the similarity, both of them will repel each other. The force of repulsion depends upon the strength of electromagnet, because this electromagnet causes induction in the ion pieces. If now polarity of electromagnet alters, means the direction of current in the coil alters. Outpoles will be induced in this end or both end pieces. Although in this case polarity alters, but still there is repulsion force acting on them. Because of nearby similar poles, hence it can be concluded that the direction of the force between the ion pieces are not changed due to change in direction of current in the coil. Now, if we make this ion piece fixed in respect to the position of the coil, and we make this ion piece free to move, then the movement of the moving ion piece can indicate the quantity of the current in the coil. If we can calibrate this movement properly in ampere scale, now if we attach one end of moving ion piece with a hinge and fix a long pointer on with this piece, the movement of the ion piece becomes rotational. If a circular scale is attached below the tip of the pointer, then the tip moves along the circular scale to give the reading of the current flowing through the coil. This movement or pointer tip on the scale depends upon quantity of the current through the coil, not on the direction of the current. Hence, this measuring system can be utilized to measure both AC and DC. The measuring instruments using this technique to measure electrical quantities are called repulsion type moving ion instruments. Repulsion type moving ion instruments are mainly used for the measurement of alternating current and voltages. Though it can also be used for DC measurements. And now we will see the actual form of repulsion type moving ion instrument. In actual construction, a hollow circular coil is used, and one of the ion pieces is attached inside the hollow coil. The other moving ion pieces or moving van is attached to the shaft controlling spring, and the pointer is also connected with the shaft. As both vans are placed in the same magnetic field, they are magnetized with the same polarity. Hence, the deflecting torque is used due to the force of repulsion, and M1 and M2 respectively. Then, the instantaneous deflecting torque F is proportional to M1 and M2, which means is proportional to H square again, where H is the field strength. If the permeability of ion is assumed constant, then H proportional to I, where I is a coil current. The instantaneous deflecting torque F is being proportional I square average deflecting torque T suffix D proportional to mean of I square over a cycle. Since the instrument in spring controlled, T suffix E is proportional to theta, whereas theta nothing but angle of deflection of the moving piece in the steady position of deflection. T suffix D equals to T suffix E. So feet or proportional mean of I square over a cycle. Thus the deflection is proportional to the square of the coil current. As the angular replacement of the moving system of the meter is proportional to the square of the current to be measured, it is proved that the instrument can be used for both AC and DC. Thank you.